All right, good morning, everybody. And our first question that we are going to be dealing with here is the distinction between washing and extraction in the context of a liquid-liquid separation procedure. Now, the whole goal of this procedure is to separate a solution with two compounds, our purple organic neutral compound and our red organic base or acid compound. And we're separating this solution into two separate solutions, our original green organic solvent with our purple organic neutral compound and our red organic base or acid compound in this new aqueous solution. And this aqueous solvent can be made of either hydrochloric acid or sodium hydroxide. Now in action, what this would mean is taking our original solution made of an organic solvent with our two compounds and putting it into this separatory funnel right here. So let's just add some of that. And what we would also be doing is adding a bit of our aqueous solvent, which again can be either one of these two substances. And so we'll add this in as well. And so after we add these two liquids, we give this funnel a shake. And after it's shaken, what we will see are two different layers due to the different densities of the liquids. So on the top, we'll have our organic, and on the bottom, we will have our aqueous phase. And so how this works is that the aqueous phase will actually protonate or deprotonate our organic base or acid in order that it will actually prefer the aqueous phase over its original organic phase. So what this would mean is our, say, organic base or acid, right here, say has a hydrogen on it. After it comes in contact with the aqueous phase, it will become deprotonated, leaving it with a negative charge, which then leaves it to actually prefer the aqueous phase. Now, you cannot deprotonate or protonate all of the organic base or acid at the same time, so you'd have to add a little bit of aqueous solvent, shake it, and then extract it through the bottom of the separatory funnel. You repeat that until you run out of your aqueous solvent.
And as a quick aside as to the mechanics of how this works is that we understand the idea of like dissolving like. So when we have our nonpolar compound and our polar compound, we can see that there is the negative charge off of the deprotonated oxygen on the polar compound, and thus it'll be attracted to any other kind of polar solvent.
Terms washing and extraction come into play are simply verbs describing the compounds that we do or we don't want. We extract what we do want, and we wash away what we don't want. For example, if we desire the red organic base or acid, by doing this liquid-liquid separation procedure, we would be extracting the organic base or acid out of its original solution, and we'd be washing away the organic neutral compound. Same thing can be seen vice versa. If we desire the neutral organic compound, we would be extracting it from its original solution, from organic fluid into its own separate solution, and we would be washing away the red organic base or acid. All right, good morning. Next question we'll be talking about is compound separation. And so what the situation we have here is we have 3 grams of this solid, equal parts glycine, adamantane, and octanoic acid. And here I've just given glycine purple, adamantane blue, and octanoic acid red colors just to distinguish them and make them easier to identify. So right here I have a few basic characteristics and properties of these individual substances. Glycine is polar, adamantane is nonpolar and will only dissolve in likewise nonpolar organic solvents. And octanoic acid is polar, it's a liquid at room temperature, and interestingly enough, it is immiscible with H2O, which is actually very useful for our procedure that we're going to be doing today. And so our first step is that we're going to be isolating adamantane, right? And so this involves 2 steps. Firstly, partially dissolving the compound in water, and secondly, gravity filtration. So let's start with dissolving it in water, right? So we have our beaker right here, got some water in there. Let's put on a hot plate with some heat and a stir bar in the middle just to speed up the process. And so what we'll actually find is that glycine being polar, will dissolve in the water. So let's just put glycine all over the place. So here we have glycine dissolved in water. The adamantane, being non-polar and only dissolving in, likewise, non-polar organic solvents, actually will not dissolve, and so it'll remain clumped up at the bottom of the beaker. There we go. And the octanoic acid, it's immiscible with water, so when we submerge this substance into water, it'll actually accumulate at the top. And given that it has a lower density than water, it will simply remain on the surface. So in this first stage, what we have here is we have all three of these different compounds in different states in the heated water in the beaker. And so next we have gravity filtration. And so what we have here is we have a stemless funnel, which will also be heated up to avoid any early crystallization. We have a ring clamp linked to a lattice rod for support. And underneath we have an Erlenmeyer flask simply to collect the samples, and the smaller opening on an Erlenmeyer flask compared to a beaker reduces evaporation. So if we were to take this water and we were to pour it through the gravity filtration, given that we have a folded filter paper right here, what we will see is that we will see the water mixture collect at the bottom of the Erlenmeyer flask, and in the filter paper, we will actually see the undissolved adamantane. Let's try that. So you have solid adamantane there, and then in this solution, just to make things consistent, we have the octanoic acid on the top, and as you're pouring through, it'll mix a little bit, but it will settle on top of the water. And we also have the dissolved glycine in the water as well. So as a first step for isolating adamantane from this triple substance solid, firstly, partially dissolve it so that they're each in different areas of the water, and then filter them out. All right. Now, to isolate glycine and oxanoic acid, we'll be utilizing liquid-liquid separation, which, just like in the first question, involves taking a solution with two compounds and separating them into two different solutions, one with an aqueous solvent, H2O, which will have our purple dissolved glycine, and one of them is a green organic solvent, diethyl ether, which will hold our oxanoic acid. Now, when we throw both of these into a separatory funnel, and when we shake the funnel up after adding these two solutions, we will see a separation of an aqueous and an organic layer. And despite octanoic acid being polar, it is readily soluble in organic substances. So we will see the octanoic acid kind of floating around, not mixing with the water, actually go into the organic diethyl ether. So by using a separatory funnel, we can quite easily separate this solution into these two solutions with different solvents. Now, one issue that we might find is that after we separate these two solutions, we might find that the diethyl ether has trace amounts of water in it, which is not an issue because we can simply add a drying agent to absorb the water, and we want to choose one that does not interact with the octanoic acid. And so one we can choose is magnesium sulfite, or MgSO4, before we take these two solutions and further isolate the substances from their solvents. Now, for the organic solvent, diethyl ether, we'll use a rotovap. And for the water solution with the glycine, we'll utilize crystallization and vacuum filtration. And so how the rotovap works is simply a round bottom flask with the solvent in it, along with the solute, the octanoic acid, And this round bottom flask is essentially heated up in a hot water bath, and a vacuum is applied to suck out any of the evaporated diethyl ether, which will in turn act as sort of an advanced efficient evaporation process. Now for recrystallization, what that involves is throwing the solution, the water with the glycine, into a beaker submerged in an ice bath. So we'll have the solvent right here, the water, along with the glycine. And as the water cools down, the water's solubility will decrease, and thus we will find crystals of glycine forming throughout the beaker. This may not happen initially, but you can just scratch the bottom of a beaker with a glass stir rod to induce crystallization. Now, after we have these two procedures in order to further isolate the solid from their solvents, for the RotoVap, we will simply have a solidified sample of octanoic acid. After a little bit of waiting, a little bit of evaporation, we'll have our isolated product there. But after recrystallization, we still have our glycine crystals in the water. So from there, we can simply use vacuum filtration, which involves a vacuum filtration flask with a unique stem for a vacuum hose, and a Buchner funnel, which allows us to readily pour in this cold crystallized glycine solution, which will in turn result in the water passing through the Buchner funnel to the bottom of the flask and leaving the glycine crystals inside the Buchner funnel. And so after we're done all of these procedures, we have our isolated octanoic acid, our solidified adamantane right here, which we can simply pull out. And we have our vacuum filtration setup, which has our isolated glycine crystals. So after isolating all of these, adamantane in first water and gravity filtration for that, and then glycine and octanoic acid through liquid-liquid separation, and then further isolating the solutes from their solvents through a RotoVap and crystallization, we have our three individual components to our initial sample.
All right, good evening. We're going to be talking about the final two questions for this third lab report involving the organic synthesis reaction and a summary of all of the techniques that we have used so far this term in our lab procedures. So to begin, we're going to talk about the organic synthesis reaction. And what is happening here is that we are having 2-naphthenol, this molecule right here on the left of figure 1, being turned into 2-butoxynaphthalene, which is this molecule on the right in figure 1. And so in this reaction, we're also utilizing sodium hydroxide and 1 iota butane, this longer chain of a molecule right here, to undergo this reaction. And so for the procedure, we take 3 initial ingredients, 2-naphthenol, sodium hydroxide, and 95% ethanol. They're weighed out and they're put into a distillation flask. This flask is then put on a hot plate with a stir bead in figure 2 right here, a diagram of this reflux setup. And then we can go about setting up the reflux setup. And what this involves is clamping down the flask and the condenser, which is inserted to the top of the flask. And we have water running through the bottom and up the top of this reflux condenser. And so as the solids dissolve, we temporarily remove the condenser and we add 0.5 milliliter of 1 iota butane. Again, that's this longer molecule in figure 1. Into the flask through a digital pipette. And when we do this, it's important to be very careful as the digital pipettes are expensive and they can easily be broken. And so after we insert the 1 iota butane, we simply put the condenser back onto the flask and we wait about 1 to 1.5 hours to let the reactants mix and allow this reaction to occur. And so after we let it sit for about 1.5 hours, the end of the reaction is marked by a reddish brown colored liquid in the flask. And so we allow that mixture to cool and we can then use it for our TLC procedure. And so right here for figure 3, we have a basic diagram of what a TLC plate will look like. And so we simply mark off 3 spots, one for R, one for the co-spot for 2 compounds, and then we have a standard to compare our reddish mixture to. So we simply take an alcohol flame and we melt a micropipette into 2 different halves, break the ends of the halves off to form 2 very, very small sort of straws almost, to allow us to apply the appropriate amount of compound to their given spots. So we have 1 compound in R and 1 compound in S, and we use both of them in the co-spot as well. We then take this plate and we dip it in hexane ethyl acetate solution in a 1:3 ratio, and we allow it to sit to allow the eluent, which is this hexane ethyl acetate, combination to rise up the TLC plate, and then from there we can analyze the results of the plate. And so after we do that, at the bottom we have we measure ice into a beaker, and we pour the rest of the cooled reddish brown mixture onto the ice. Once it cools, we will see the quenching reaction take place, which involves a substitution reaction to occur and allow a precipitate to form. We can then isolate the solidified precipitate through vacuum filtration, and then we have our solid product. And so when we analyze the product, which is 2-butoxynaphthalene, we can see that it's a light orangish colored powder, and an IR spec confirms this identity. And so when we find an IR spectroscopy sample of 2-butoxynaphthalene, we can observe its functional groups, such as an OH group at around 3,000, and we see its aromatic rings around the 15,000 range right here. Now, further analyzing the product and the TLC plate that we formed, we can see that right here, there's some slight contamination of the standard, and we can see major contamination where we administered our product of the reflux reaction. And so as again, right here, we have to see 2 major spots and 1 additional spot. And the reason why we do not consider these contaminants in the co-spot is because we administered both at the same time. Now, what type of reaction is happening, SN1 or SN2? And so in our SN2 reactions, we see the iodine from 1-iodobutane leaving as the leaving group, which then leaves this butyl group to act as a nucleophile. The hydroxyl group then gets slightly deprotonated from the sodium hydroxide, which allows this transition state to occur. And this transition state and the forming and leaving of this transition state marks as the rate determining step for our reaction. And so in SN2 reactions, right here is an example of the transition state forming. We see the H from the OH group being deprotonated by the sodium hydroxide, and we see the butyl group attacking the electrophile right here, which is the now negatively charged OH group once the hydrogen leaves, which gives us our product of 2-butoxynaphthalene. Now for question 4, for a summary of all the techniques that we've utilized, our first that we're going to talk about is recrystallization and filtration, and they're often paired together simply because of how we extract solids from a solvent. And so through recrystallization, we use this technique to purify a solid sample. And through recrystallization, because we must first dissolve the solid, we can find out what solvents work best for the solid. And what kind of solvent we're looking for is one that does not dissolve the solid at a low temperature, but does dissolve the solid at a higher temperature. And so after we undergo this procedure, if an undissolved solid still remains in the solvent, even after it's been heated up, then we can allow it to cool, and then we can use gravity filtration, which allows us to separate insoluble solids from the mixture. And if the solid does dissolve in the solvent, then we can cool it down, put it into an ice bath, and we now have crystallization and recrystallization of a pure solid, as that is the purpose of recrystallization. And we can then use a second form of filtration, such as vacuum filtration, to isolate the crystals from the solvent. The next technique we're going to talk about is thin layer chromatography, or TLC. And again, this is an example of our TLC plate from the Organic Synthesis online lab. And these TLC plates can be used to determine a number of things. Purity, if contaminants are present, such as with the standard, we can see a darker kind of marking indicating contaminant. We can identify a component in identical situations through RF calculations. And what that means is that the difference from a spot to the eluent front, which is the end point of where the hexane and ethyl acetate solution rises up the plate, the difference and the distance that it traveled, we can indicate and suggest that they could be the same compound. And finally, we can also use it to monitor the progress of reaction based on the polarity of whatever sample we are applying to the TLC plate. The third example is distillation, and of the three types, only one was demonstrated in the lab, which is simple distillation. And it's used to either separate two liquids from a sample or a solid from a liquid. And by doing this, the liquid left over is highly concentrated, and liquid separated, in the case of separating two liquids, are both highly concentrated. Now, one thing that we can observe while undergoing simple distillation is a boiling point at where the solution begins to boil. And by a broader indicates contamination, and a narrower boiling point or boiling point range indicates a more pure sample. This sample can then be utilized for a TLC plate or IR spectroscopy to find out more about the compounds that we are working with. Now, the fourth technique that we utilized is gas chromatography. And gas chromatography can be used to identify different compounds. Now, in figure 8 on the right, we have an example of a chromatogram, which is generated through gas chromatography. And based on the retention time, which is the time of the peak of the final signal, we can use that to identify unique compounds. And an additional piece of information that we can deduce from gas chromatography is that through an integration ratio calculation of the areas underneath the signals, we can use that equation to calculate a concentration of a sample being put through a gas chromatography. The third example of a technique that we utilize in the lab is IR spectroscopy. And this is a very common procedure done to essentially distinguish different functional groups. So if we're going to look at the IR spectroscopy of the fifth technique that we utilized in the labs this term was IR spectroscopy, which is a very common procedure. It's very simple. We simply analyze the amount of absorption and reflection based on different functional groups of a compound. So if we use the same example of 2-butoxynaphthalene, the procedure that we use in the lab this term is IR spectroscopy, which is a very common procedure used to identify different functional groups of a compound that we are analyzing. So if we use the same example of 2-butoxynaphthalene, we can see its OH group around 3000, and we can see its aromatic rings around 1500. And this is very common. What we're doing is we're analyzing the absorption and reflection of light at different wave numbers of different aspects of a compound. The sixth and final technique we use in the lab this term is an organic synthesis reaction, and analyzing what kind of reaction is going on. And it tells us if a substitution reaction is SN1 or SN2, and we can find this pretty much based on a substrate's structure. And so if it's an SN1 reaction, two products will result into a racemic mixture, and this comes from the fact that the nucleophile can attack from two different sides of a stereocenter, resulting in two different potential products. And an SN2 reaction results in only one product, with a nucleophile attacking the electrophile, with only one attachment site possible, rendering only one product and a non-racemic mixture. Now, here are the references for the videos and for this PowerPoint presentation. Thank you, and I hope you have a good day.